Now let's solve question 2. Let's look at question 2 first. So it is suggested that the following function of v, that is f of v, equals to e raised to the power minus mod of v. Also we are given f of v equals to sine v whole square by v squared, and we are given f of v equals to 1 if mod of v is less equals to alpha, and 0 if mod of v greater than alpha. So we are stated that this f of v may represent an autocorrelation function of a wide sense stationary stochastic process by setting v equals to tau, or may represent a spectral density function by setting v equals to omega, or it may represent both. So we need to show that for which conditions these statements are valid. So let's look at the solution now. So we will use this fact that we know for a real wide sense stationary stochastic process, R of tau is must be even, and R of tau is less equals to R of 0, and also its power spectral density S of omega is even and positive. So these two statements actually proved in question 1. So now let's look at first function. So f of v equals to e power of minus mod v. So we see this is an even function. So and also e power of minus mod tau less equals to e power of minus mod 0, that is 1. So this may represent this can represent autocorrelation function. Now let's look at the possibility of power spectral density. So we know that power spectral density is even. So if we replace v by omega, we see that e power of minus mod omega is also even, and e power of minus mod omega is also greater than 0. So this may also represent a power spectral density. Now let's look at the second function. The second function is given as sine square tau by tau square. So we see that sine square tau by tau square, this is actually can be written as sine by tau whole square, which is always even. And we see that if we take the limiting case, that is tau tends to 0, we get 1, and this value quantity is always less equals to 1. So the condition satisfies that this is even, and R of tau is less equals to R of 0. So this can successfully represent the autocorrelation function. Now let's look at the possibility of representing a power spectrum. So if we replace tau by omega, we get sine square omega by omega square, which is of course even because it's a whole square term, and also as it is whole square, it is always greater or equals to 0. So we see that this may also represent a power spectral density. Now let's look at the third option. So we are given that f of v is 1 if mod of v is less equals to 1, less equals to alpha, and equals to 0 if mod of v greater than alpha. So we see that it cannot represent an autocorrelation function. Why? Because if we take the Fourier transform, we will get 2 sine alpha omega by omega, but that is not negative, that is not non-negative. So this, as this is not an even function, this is an odd function, so this can give us values, negative values, so this cannot be an autocorrelation function. Now let's look at the possibility of a power spectral density. So we see that f of omega is actually always even, because we have only two values for f of omega, 1 and 0, so this is always even, and f of omega is always greater than 0 because it can take only two values, 1 and 0. So this can successfully represent a power spectral density function. So that's it for question 2. Thank you.